Good evening, ladies and gentlemen, attending measurements for BTech subject at Vaal University of Technology. The purpose of this video is to actually do a small experiment and compare two commercial type cables in terms of their frequency loss across a range of frequencies. The setup that I've got here is very simple. In the black box, in my cage here, I've got two rolls of commercial cable, brand new, and they've been set up to be connected. So they are of unknown brand and unknown specification. All that we know is that there are 50 ohm impedance, and the one is a thin cable and the other one is a thick cable, and that's about all that we can physically see from this setup. We're going to take the cables and scan it through a range of frequencies, expecting to see how the frequency change does affect what comes out of the cable. The setup is very simple. I've got a vector voltmeter, which is a special voltmeter for measuring voltages across a range of frequencies. And then I have a radio signal generator that can go up to 2.4 gigahertz, and we're going to choose a certain frequency intervals, and at each frequency interval we're going to give you a chance to take down the reading here. On the display of the vector voltmeter, we have channel A and channel B, and channel A then gives me, after my feed line and everything else, it gives me my voltage that is going into the cable, and as a result going out of the cable on channel B, and simultaneously I can then see what is the output cable voltage. So as we have set up this cable 1 at this stage, at 1 megahertz, I'm putting in 785 millivolts, which is really not important to us. This value is important. And coming out of the cable, I get 722 millivolts. So going into the cable, 730 millivolts, and coming out slightly less because of cable loss, 722 millivolts. If I go back and I change my carrier frequency, you'll notice the instrument on the vector voltmeter is adjusting. And just for demonstration purpose right now, if I choose a frequency like that, 200 megahertz, I need to adjust the RF level, and if I'm lucky I can do that, so that we can get back to 730 millivolts. Now it's very critical for your experiments that you put as close as possible to that input voltage being the same, because you're going to compare it apples to apples. So that's about the closest I can get it at this stage. We will live with that, it's close enough. Notice that I'm actually putting much more, but I had to adjust to make sure that channel 1 is exactly this. And now I have this reading for my reading that is going on. Once we got that, we can choose all kinds of frequencies, and we need to adjust channel A every time so that the readings can be done accurately. So, starting at 50 megahertz carrier, 50 megahertz is around about here. Then RF level, we make sure we get a starting point. It can be anything. Doesn't need to be 730 for your first reading, but since we have already started and we've got something useful there, let's choose that one. It's quite within the range of our instruments, and let's make it easier, round number, 500 millivolts or thereabouts at 50 megahertz. Carrier 50 megahertz, like this. Right, RF level, just go like that. That's the closest to 500 millivolts we will get it. And your first reading out is 491 at 50 megahertz. The phase angle minus 18.5 degrees. Then we choose the next frequency, which will be 100 megahertz. And this is now really the experiment in action. 100 megahertz, you will notice already there's been a change. Remember, the input cable between the oscillator and the cable input does have an influence, but to make sure that that influence is not affecting our readings. We adjust the signal generator to get close to 500 millivolts, and now I get 453 and the phase angle minus 39.5. The next frequency on my list here is to go 200 megahertz. 200 megahertz, RF level. Need to adjust it back to 500 millivolts so that we can compare apples to apples. Your graphs will be in dBs. The angle now minus 98, almost 90 degrees, and the amplitude 108.7. So what do we see? We start seeing a decline in amplitude, and we saw an increase in the phase angle. Next frequency I would like to look at is a nice leap into the future, 400 megahertz. And that's about it, 400. Again, making sure that the input channel, channel A, is set up correctly. Let me just make sure that I'm adjusting what I need to adjust. As close as you can get it to 500 millivolts is fine. That's about it. How about that? So from 100 millivolts it drops to 29.9 millivolts. The phase angle sweeping right over to minus 108.3 degrees. Then we go to the next input frequency, 700 megahertz. You see where this cable is going with its readings? You could have taken frequencies in between and so on. I'm quite happy with this range of frequencies because we want to see the effect. And then we notice our input has changed again, so we make sure it goes back to as close as possible to 500. How about that? 9.21 millivolts, phase angle of minus 31.4. And we go to 900 megahertz. By the way, you can punch in the number as well. We'll jump immediately there. You'll notice this one is out, so check for the level, and we'll just get it as close as you can to 500, and amplitude now 1.295 and 500 millivolts input, and the phase angle now minus 78.3. So the phase angle went in and out. So interesting things, these phase angles. And then we end at 1 gigahertz. 1 gigahertz, I'm quite happy with that. Remember, we need to check channel A, must be the same. The experiment does not work if you change your input voltage with every reading, because then no graph is going to make sense and you're not comparing apples to apples. By doing this, now the cable is actually slightly improved, can you believe it? So it seems to be liking microwave frequencies. That's cable 1. Now we're going to start all over. Let's go there, and then go there, and over there, 1 megahertz. But now, instead of cable 1, we're going to measure the second cable. We want to compare the two cables. Hence, the same readings, the same frequency steps, but we are expecting different readings. Now again, we're going to start with the same channel A level. So RF level here, bring it down to 500. Doesn't help you do it now 600 all the way, because you need to compare apples to apples. So, setup, basic. Signal generator generates signal, goes into the cable. It also is measured by the vector voltmeter. It shows me channel A is about 500 millivolts. The output, the result from the cable, is then on channel B, and that is exactly the same. So now that we know the setup works, our first frequency that we put in, carrier, is 50 megahertz. You'll notice immediately there is a decrease because of our feeding cable. How do I fix it? Very simple, RF level, adjust it until we get 500 millivolts. Just make it nice and easy. Right, that's almost there. You have to be patient with this thing and just touch it. It's like a nice, easy way of doing that. Close as you can get. Yeah, it's close. Closer the better. Further away, the more error you are building it in. Okay, let's settle for that. And I now have 286 millivolts with a phase angle of 109.7. Second frequency, 100 megahertz. So carrier, and we are just going for a 100 megahertz. The RF level, make sure that you are putting on channel A. The same going into the cable, 500 millivolts, or as close as you can. This one is very finicky, but it works. That's close enough. And now I've got 122.6, and the phase angle minus 170.2. Then we go for 200 megahertz, which is around about here. Man, I love this experiment. Teaches you patience, teaches you opportunities to measure many things over and over. 400 is wrong, no? We're going for 500. Or very close. It's close. You see? Okay. Can split hairs about this one, but that gives me a reading 102.7 and 74 millivolts. Just check your phase again. It's a positive angle in this case. It's not negative anymore. So somewhere it flipped over. Right. Then we go for 400. No, I lie. 400 megahertz. Like that. Make sure that channel 1 is 500 millivolts. Or close. That's nice. Now I've got 11.78 millivolts and the phase is 14.7 degrees. So it's a positive angle in this cable. Then our next reading is to be taken at 700 megahertz. And we make sure channel A should be where? By now you should know. 500 millivolts. As long as it's the same. It could have been 300 millivolts for the whole experiment. Doesn't matter. As long as you keep it the same. Because you want to compare inputs with inputs and outputs with outputs. So at 500 millivolt going in, 11.4 or 0.4 coming out, and my phase angle minus 32.9. So now it's gone from positive angle to a minus angle. And luckily that is one of the questions of the experiments. Why the heck is this happening? Our next frequency, 900 megahertz. So like that. Change the RF level. Make sure that you are getting 500 millivolts or very close. And then our reading, 0.035. And the phase angle now minus 98.7. Interesting. And the last one then, our carrier frequency 1 gigahertz, and the RF level, keep sure it's keeping it like this. You'll notice the more we use the instrument, the easier the buttons become. So that's also quite nice. Okay, that's about as close. The angle minus 12.4. Amplitude 1.703. So that concludes the physical measurements, and then I would like you to calculate the losses of both cables, compare it to each other, graph the frequency to loss relationship on both cables, put it on the same graph. You can use the spreadsheet, you can use any type of computer software to do that, and then you answer for me the relevant questions as per the study guide. Thank you very much.